So now we'll see the case of designing the state feedback controller for the multivariable case. So far we have discussed the designing of the controller mainly for the single input variable case, where we have also discussed the robustness and tracking problems. So for the multivariable case, the layout of the problem would remain the same. So consider a plant described by the n-dimensional p input state equation. So now here we are considering p number of inputs instead of scalar, given by this state equation where a, b, c are the matrices. So you will note that when we were discussing about the single variable case, the parameters we had taken in a small letters. So now when we consider the case of the matrices, we will consider those parameters as the capital letters, as you will see in B and C matrix. In the state feedback, so we denote this as the plant, and in state feedback the input u is given by this one. So we have seen earlier for the single variable case we have designed such kind of input, but now here the k would be matrix instead of vector. So k is a p cross n times a real constant matrix, and r is a reference signal. So once we put this u into this plant, we obtain the state space equation for the closed loop system. That is, the A matrix would now change to A minus B times K. The B matrix would remain the same, but it now becomes a distribution matrix of the reference signal, and there would not be any change on the C matrix. Okay, so here we will discuss cases, or we'll discuss some designs to synthesize this K. So again, recalling the important theorems or the important results what we had discussed for the single variable case. So for the multivariable case, the pair A minus Bk comma B for any P cross N real constant matrix K is controllable if and only if the pair AB is controllable. So this is the key result, and in fact this is the starting point as well. So if the pair AB is not controllable, we cannot ensure that the closed loop pair would also be controllable. If we see a very quick snapshot of the proof of this theorem, the proof would remain almost similar to what we had seen for the single variable case, but for the multivariable case only this matrix would change. So if you recall that the controllability matrix of the feedback loop we have expressed as equal to the controllability matrix of the plant times some constant matrix. Now here, since we have the p number of inputs, this controllability matrix would no longer be a square matrix, but it is ensured that the rank of this matrix is full rank. So if you see the rightmost part of this equation, this is an upper triangular matrix with all the diagonal elements as the identity matrix of p dimension. So this matrix would be a square matrix and would definitely be a non-singular matrix. Now to ensure that the CF is also full rank, we only need to have the full rank of this controllability matrix of the plant. So only this part would remain changed. Otherwise, the rest of the part would be similar. So another conclusion we made at that time, that the controllability property would be preserved in any state feedback if the original plant is of the original pair is controllable, then under any K the pair A minus Bk comma B would also be controllable. But at the same time, we also notice that the observability property, which we would discuss in the subsequent week, is not necessary be preserved. The next result says that all the eigenvalues of the closed loop state matrix can be assigned arbitrarily provided complex conjugate eigenvalues assigned in pairs by selecting a real constant k if and only if the pair AB is controllable. So again, this is the similar result we had discussed for the single variable case, for the single input variable case, but this also holds for the multivariable case also, that that if the pair AB is controllable, then the eigenvalues can be placed anywhere. Now, we had also discussed that if the pair AB is not controllable, then we can use the uncontrollable decomposition to apply on this pair AB and extract only the controllable part. So we only need to show to ensure that the uncontrollable component in that decomposition has its eigenvalues onto the left hand side, right? Because for the controllable part we can place the eigenvalues anywhere on the right hand side, but if we cannot uh, change the eigenvalues of the uncontrollable part. So if we ensure that the eigenvalues are on the left hand side, then the system, at least we can ensure the stability of the system. Okay, so for the single input case, we had discussed two design for the design of the state feedback controller. So the first one, if you recall, is the eigenvalue assignment, and the second one is using the Lyapunov equation method. Now, if you recall that in the eigenvalue assignment method, we computed the feedback gain by taking the inverse of the controllability matrix. Now, since the controllability matrix here is not a square matrix, we cannot take its inverse. So the eigenvalue assignment approach cannot be applied for the multivariable case to synthesize the gain matrix K. So, but in the Lyapunov equation method, we had seen we do not require the inverse of the controllability matrix, but it is the inverse of some another uh, square matrix, which we will see that whether that method applies directly for the multivariable case. So if we see this problem of designing a feedback controller, says that consider an n-dimensional p input pair a comma b. We need to compute a p cross n real constant matrix k so that a minus bk has any set of desired eigenvalues. Now this method has some restrictions, that the desired eigenvalues cannot be placed at the origin, and also the set of desired eigenvalues should not contain the eigenvalues of the A matrix also. Okay. Let's see the design of the gain matrix K. So the first three steps remains almost similar, which says that first of all we need to form matrix F, which is a square matrix of dimension n, which contains a set of desired eigenvalues, and at the same time it should not contain the eigenvalues of the original A matrix. So we had discussed number of forms for selecting a matrix F. One is the model form and another is the companion form. You can choose the matrix F in any of the form. The second step, we need to select an arbitrary p times n matrix k bar such that the pair F transpose k bar transpose is controllable. Third step, once we have found such k bar, then using this Lyapunov equation, we can solve for a unique matrix T. Now from here, once we have computed this T matrix, then the design of the gain matrix was given by this one, and the key result hinges upon the invertibility of the non-singularity of the T matrix. So we need to ensure that for the multivariable case, is it always possible that the matrix T is non-singular so that we can take its inverse. So we know that if the matrix T is singular, then we cannot carry forward this design because we cannot compute this equation. So in that case, since k bar is chosen arbitrarily, we would keep repeating the design until we find a T which is non-singular. Okay. And if the matrix T is non-singular, we can compute this, and at the same time we ensure that the closed loop state matrix would have the set of desired eigenvalues. And the proof of this one we can see straightforwardly, that we just need to put k bar is equal to kt into this equation, and we obtain this. And finally we can write the closed loop state matrix as T into F into T inverse, which is basically the similarity transformation, which ensures that whatever the eigenvalues this F matrix has, the closed loop state matrix would also have those eigenvalues. Okay. Now the most important aspect here, that under the SISO case, the single input single output case, we had ensured that the T matrix would always be a non-singular matrix. But for the multivariable case, it might not be possible that the matrix is non-singular even if the pair AB and F transpose K bar transpose are controllable. Hmm. So we will see the proof of this one, that why we cannot ensure always the non-singularity of the matrix T in the multivariable case. So in fact this leads to the only the necessary condition, meaning to say that if the matrix T is non-singular, or the determinant of the matrix T is not equal to 0, then it implies the both the pairs A comma B and F transpose comma K bar transpose would be controllable. But if this condition holds, that both the pairs are controllable, that then it might not be possible that the matrix is non-singular. Okay, so this is only a necessary condition but not a sufficient condition. We can also write this statement, and as one of the results of which the proof we will see, that if A and F have no eigenvalues in common, then the unique solution T of this Lyapunov equation is non-singular only if the pairs A comma B and F transpose K bar transpose are controllable, so which is only a necessary condition. So we can see the proof, which is again the same as what we had discussed for the single input variable case. So if you recall, we had obtained this equation as the final equation to show the matrix T, or to comment on the non-singularity of the matrix T. Now this part, delta of A and delta of S is basically the characteristic polynomial, and by using the Cayley-Hamilton theorem, this part would go to 0. So the remaining part is minus T times delta of F. So this is another matrix which we had defined, if you remember, this by F tilde. Okay. And on the right hand side, we have the controllability matrix of the pair A comma B, the controllability matrix of the pair F transpose K bar transpose, and in the middle we had a square matrix which is a non-singular. So now if we see this for the multivariable case, all the small b's would change into the capital B's. Similarly here, all the small k bars would change into the capital K bars, and all these ones would change to the identity matrix of appropriate dimension. So this can be represented as finally the controllability matrix of the pair AB times some sigma matrix, which is this one, times the controllability matrix of the pair F transpose K bar transpose. Okay. Now this matrix would be having a dimension np times np. This matrix would have the dimension np times n, and this matrix would have the dimension n times np. Okay. Also note that this is an upper triangular matrix. So this matrix would always be a non-singular matrix, and the determinant would be equal to identity. Okay. Now the rank of this matrix is n because it is controllable. The rank of this matrix would also be n. So, and on the left hand side, delta or f tilde, we had already shown that this matrix is a non-singular matrix. Okay, so we can take its inverse and it would be a square matrix also. So now if this is control, if this has full rank, this is a square matrix and this is also a full rank matrix, then we cannot ensure that the matrix T would still be a non-singular matrix. But if the matrix T is a non-singular matrix, we can ensure that all these matrices would be of full rank. Right? We can, so we can see one example also. Let's say the controllability matrix, or let's write minus T f tilde, which is delta f, as the controllability matrix of the pair AB sigma and the controllability matrix of the pair F transpose comma K bar transpose. Right? So let's write this. Let's take some basic example to demonstrate this fact. So we take two states and two inputs. So in that case, this matrix would have the dimension 2 cross 4, and that 2 cross 4 matrix can be written as this one. Okay, now this matrix is a full rank matrix of dimension 2. This we can choose an identity matrix of dimension np times np sigma, and this controllability matrix of this pair would be of dimension 4 times 4 cross 2. Okay, and np is 4, so basically this would be 4 times 4, and this we can write as 1 0. Okay, so this matrix has full rank, this matrix has full rank, this is a non-singular matrix. So now if we see the product of all these matrices, it would be 1 0, right? So you see on the right hand side, we do not have the full rank matrix, though all the three individual matrices are of full rank. So we cannot ensure that the T matrix would be a non-singular matrix. Okay, so that's why this is only a sufficient condition, oh sorry, a necessary condition, but not the sufficient condition. So now the problem arises that either we keep iterating to find those k bar such that two conditions are satisfied, that the pair F transpose K bar transpose is controllable and the matrix T is non-singular. Okay, or we should search for another design method by which we can compute in one shot the matrix K. So for that we will carry out another design which we also call the cyclic design. So the idea here is that we change the multi-input problem into a single input problem, and then we apply earlier results to finally compute the matrix K. Okay, because for the benefit of the using this cyclic design, that once we have represented a multivariable system or multi-input variable system into a single input variable system, then all the previous results, the eigenvalue assignment and the Lyapunov-based design, we could apply to finally compute state feedback for a multi-input problem. So we define a matrix A as a cyclic matrix whenever its characteristic polynomial equal its minimal polynomial. So characteristic polynomial we have been discussing a number of times, but the minimal polynomial we had discussed during the stability week. Possibly in some of the earlier lectures we had discussed that what polynomials we can say that this polynomial is a minimal polynomial. Okay. Now the same definition we can also apply by transforming the matrix into its Jordan form and then applying then seeing the conditions being satisfied by the Jordan form of the A matrix. So a matrix A is called a cyclic matrix whenever the Jordan form of A matrix has one and only Jordan block associated with each distinct eigenvalue. Okay. So this is how we define the cyclic matrix. Either you compute the characteristic and minimal polynomial and see their equivalence, or you transform by using the simulated transformation into the Jordan form, and then seeing whether there is only one and only one Jordan block associated with each distinct eigenvalue. Okay. So let's see. So this is one of the important results which we will use to design the gain matrix K. So if the n-dimensional P input pair A comma B is controllable, and if A is cyclic, then for almost any P cross L vector V, the single input pair A comma BB is controllable. So this single input pair would possible if we have this P cross 1. Okay. Then this single input pair A comma B times V is controllable. So if we recall from the controllability week, we had discussed one result that the controllability property of the system is invariant or is invariant under any simulated transformation. So whether if we have transformed into another equivalent transformation, uh, the Jordan form of the matrix A would still be satisfy the controllability of the pair A comma B. Okay. We will not go into the detailed proof of this result, but we can see through some example or the logical idea behind this proof. So for example, consider this A matrix which is a 5 cross 5 matrix, and B is 5 cross 2 matrix, meaning to say that we have 5 states and 2 number of inputs. Okay. So if we pay attention to this matrix A is already given into its Jordan form. So and it contains 2 distinct eigenvalues. In overall, it contains 5 eigenvalues, but has only 2 distinct eigenvalues. One is 2 and another is -1. So with respect to -1, we have one block, which is a Jordan block, and with respect to the eigenvalue 2, we have another Jordan block. Okay. So this satisfies the definition of a cyclic matrix. So we can say that matrix A is a cyclic matrix. Now let's select V, which is 2 cross 1, and we can write this B times V as vector this one. So this cross elements represent that it can represent any of the that we are not concerned with these elements. So these elements could be pretty much straightforward if you want to compute from here. So this one would be V2, this would be 0. Let's denote the third element by alpha. The fourth element would be 4v1 plus 3v2, and let's denote the fifth element by beta. Okay. Now one of the problems we had discussed during the tutorial of the controllability week, that the necessary and sufficient condition for the pair A comma B times V to be controllable are that alpha and beta should not be equal to 0. In fact, this is also one of the results of which the proof we had seen through numerical examples during the tutorial classes, or you can prove by yourself as well. So now see, since alpha is given by V1 plus 2 into V2 and beta is nothing but only V1, now either alpha or beta is 0 if and only if V1 is equal to 0, or V1 by V2 is equal to -2 by V1. This you can see readily, that if V1 is 0, beta would straightforwardly be 0. If beta is 0, then the pair A comma B times V is not controllable and we cannot carry forward our design. Now, if V1 over V2 satisfies or becomes equal to minus 2, then in that case, uh, the alpha will become equal to 0. Again, according to this result, the pair A comma B times V is again not controllable. Okay. But see, thus any V other than V equal 0 and V1 equal minus 2 times V2 will make A comma B times V controllable. Okay. We can visualize this in a two-dimensional space because we have only two variables V1 and V2. So the first condition is V1 equals 0, which is this line. Okay, along this line V1 would always be 0. Now another condition is that V1 by V2 should not be equal to minus V2. So we have normalized the x-axis by V1 by 2 and all the V's should also not lie onto this line. Now if this V lies any other elsewhere on this two-dimensional space, then it is guaranteed that the pair A comma B times V is controllable. Okay, so these are the almost the rare chances. So the cyclicity assumption is only is essential for in this theorem. We can take another example also. Let's take this pair as this one, okay, which is a 3 cross 3 dimension, and B again contains two number of inputs. Now this A matrix has eigenvalues, has three eigenvalues located at 2. Okay, but it has two Jordan blocks with respect to one eigenvalue. So one block is this one, another block is this one. So here, although the pair A comma B is controllable, but the matrix A is not cyclic. So for any V, so there is no V such that you can make A comma B times V controllable. So we need the controllability of this pair to carry forward our design of the gain matrix K. If all the eigenvalues of A are distinct, then it is already ensured that there would be only one Jordan block associated to every eigenvalue. So thus a sufficient condition for A to be cyclic is that all eigenvalues of A are distinct, right? So this is pretty much straightforward. It is only a problem if the matrix A has repeated eigenvalues. So we need to see whether there is only one Jordan block associated to the repeated eigenvalue. Okay. Now the next result says that if the pair A comma B is controllable, then for almost any P cross N real constant matrix K, the closed loop state matrix has only distinct eigenvalues and is consequently cyclic. So here we see the straightforward benefit that in the Lyapunov based design, we need to select the matrix K bar to ensure those two strict conditions. But here we had seen that we can select almost or for almost all P V vector, the pair A comma B times V is controllable. Now, if the pair A comma B is controllable, then for almost any matrix K, we can put any matrix K such that this matrix would have the distinct eigenvalues and would definitely be a cyclic matrix. So this is the main benefit, that there we need to iterate for those K bar, but here this the become or distinct eigenvalues closed loop state matrix has only distinct eigenvalues for almost all K. Now with the distinct eigenvalues, we also ensured at the same time that so this condition is pretty much straightforward, that it would be cyclic because it contains all the distinct eigenvalues. Now we will use these two important results to finally design that the K matrix. First, but note that in both these results, we need the controllability of the pair A comma B. Now, if the original pair A comma B is not controllable, from the necessary and sufficient condition, it is already ensured that you cannot design a K matrix to place the eigenvalues arbitrarily. So, if the pair is controllable and A is cyclic, we can select any B such that this pair is controllable. Now, if this pair is controllable, we can select any K matrix of appropriate dimension such that this matrix has distinct eigenvalues or it becomes cyclic. Okay. So we can now find the K matrix to place all eigenvalues of this closed loop state matrix in any desired position. So let's see. So first case, consider that if the matrix A is not cyclic. Okay. Now if the matrix A is cyclic, we can directly go to the step 2. This you can see as the step 1, which we need to carry out if the matrix A is not cyclic. Now by using the second result, we can get rid of this non-cyclicity of the matrix A because we can select any K to make this closed loop state feedback matrix to make this pair as a cyclic matrix. So let's see how this is implemented through the block diagram. This is the original plan. Okay, this is the original plan. Now this step 1 is carried out if the matrix A is not cyclic. So first we introduce a feedback by this equation where W is some variable, U is equal to W minus K1x, such that the matrix A bar, which is defined as A minus B times K1, in this state equation becomes cyclic. And this is a result, or this is a consequence of the second result, this one, second theorem. Okay, so now we had ensured two things, that this, if I see the map from W to Y or W to X, from W to X, so I can carry out my design on this map from W to X instead of U to X, because U to X, in this map U to X, we do not have this matrix A as a cyclic matrix, but in the map from W to X we have the state matrix as a cyclic matrix. Now because the pair A comma B is controllable, so A bar B would also be controllable. Thus there exists a P times 1 real vector V such that A bar comma B times V is controllable. Now note that here the selection of the matrix K1 and the selection of the vector V is not unique, because this was the conclusion of the previous two results also. Okay, so the choice of K1 and V are not unique and they can be chosen arbitrarily. Let's carry forward. So next we introduce another state feedback where now we compute W as the reference signal R, which is given, minus K2 times the state X, with K2 defined as V times K. So now you see that K is now a vector which we need to synthesize finally instead of the K matrix, where K is a 1 cross n real vector. Then applying this controller to the previous system, we obtain this state space equation of the closed loop. So in the block diagram you would say from the X, so we have added this block or this path to finally compute this W. So the step 1 is to carry out this part, and this step 1 was carried out if the matrix A is not cyclic. Now if the matrix A is cyclic, we can directly carry out the step 2. Okay, so this would become as the closed loop state matrix A bar minus B times V times K, and B becomes the distribution matrix of the reference signal R. Now, because the single input pair A bar comma B times V is controllable, the eigenvalues of this matrix of the closed loop state matrix can be assigned arbitrarily by selecting a K. So since we only need to design this vector K, which we can carry out by either using the eigenvalue assignment approach or the Lyapunov Bayes approach, where both the conditions would be satisfied. First, the controllability matrix would be a square matrix. Second, the matrix T in the Lyapunov design would always be non-singular. So now if we combine these two state feedbacks, so first was this one W is equal to R minus the first one was U is equal to W minus K1x, and the second one is the W is equal to R minus K2x. So combining this one, because we finally need to compute the signal U, is given by R minus K1 plus K2 times x, and K1 plus K2 would give me the complete matrix K. Okay. Now with the help of this K matrix, we can achieve arbitrary eigenvalue assignment. Okay. So this is how we can carry out the design.